Perfeito.
So welcome to the last session of today. And our first speaker is Tiago Pereira from the University of São Paulo.
Good afternoon. It's a pleasure to be here and share some of the work I've been doing in the past 3 years. I would like to thank the organizers for the opportunity. So this work is mainly done by Ulrike Feudel. So he's a seriously good guy. So he's been cracking this work quite hard. I would like just to make a general introduction because this is a very general audience. I think the whole gray you see here is to try to describe the network dynamics, some kind of feeling of statistical physics is starting from what we call the microscopic information of the system. So I call a network or dynamical system, which is a bit more than a network, is this triple here, where G tells who is neighboring to whom, is the graph structure. F is the local dynamics at each node. So I'm thinking that at the top of each node of this network, I have a dynamical system, which is interacting through G, which is the graph. And A is the coupling function, so who dictates who's talking to whom, okay? So this is a very classical setting. For example, in the heart, you can think of heart cells as being modeled by periodic oscillations. Okay? So each has its own frequency. A, which is how they talk to each other, will be via diffusion. And G is some kind of a lattice, very regular graph. And here is very important, the collective dynamics for proper functioning. So this is a very classical example. Another one, there are many people in this audience that they're experts in this, are power grids. So here again, near power balance, F can be modeled as a periodic dynamics. A is again diffusion. Diffusion, I mean that the coupling only depends on the difference of states. And G, which is the graph, is usually very complicated, but it's okay. So here again, frequency synchronization is quite important for this problem to keep power balance. And another example is of this triple is in neural networks, as we've seen here today. Here, F can be either periodic or chaotic. I'll be focusing on periodic motion. A, there are only two types, is either electrical, which is diffusive, by the way, and chemical. And G is usually very complicated. But again, here, collective dynamics. So I start this network, I make them interact. They can have a transition to a collective state. This is very important to this problem. So my main assumption here is the following. So when I analyze a node in isolation, this node is periodic, is near Hopf bifurcation, whatever that means. And I have a shear in my oscillator. If you like mathematics, shear means like if you do this normal form reduction, the first Lyapunov coefficient is complex. If you don't like this, you can think of that the frequency depends on the amplitude. So I have a periodic motion where the frequency depends on the amplitude. And I start my setting where I couple these guys now together. It doesn't really matter the way I couple them very much now. So I couple them together, and there is no synchronization. This means that each oscillator has its own frequencies doing something crazy, okay? So nothing is really going on. So what I do next, I pump noise into the network. Is it clear? So I have a network of periodic oscillations when isolated. Now nothing happens. So let's say I had total chaos before. So now I pump noise in the network. So what happens is that the noise leads to an adaptation, and I have a collective state emerging. Okay? So it's very important that you have hubs here. If you don't have hubs, this effect does not appear. And you have to pump noise everywhere. So it's some kind of transition to synchronization. This is the phenomenon I want to explain. But if you're too greedy, what will happen? Maybe you think the more the merrier. Okay, let me pump a bit more noise. So you pump a bit more noise. So what do you think is going to happen if noise improves? Any guesses? So the problem is the following. I had a system. Deterministic system does not synchronize. I pump noise. I have a transition to synchrony. Then I pump more noise. What will happen? So what will happen is that pumping stronger noise destroys the synchronization effect. So it's somehow a nonlinear behavior. Yeah? Is it clear? This is the problem I want to discuss. So shear plays a big role here. So because we will introduce multiple timescales into the problem, these multiple timescales, they will be very important for the analysis. And somehow there's an optimal noise strength. Yeah? So if you achieve this optimal noise strength, then you're in good shape. Otherwise, you're not in good shape. OK. So let me tell you how we think about this model and how we model this. So I start with exponentially attracting periodic orbit. Here's for the isolated system. When the system is isolated, I assume that I have an exponentially stable periodic orbit. I can parameterize this orbit through the phases. OK, this will be my main variable for many, many important reasons. So now I'm assuming that this orbit is born from a Hopf bifurcation. So this basically means like this orbit is very circular if you look at the orbit, is basically what it means. I have shear in the oscillator, so you think of the frequency of this orbit depends on the amplitude. And I will include noise, and actually this, just to facilitate my analysis, I will think the noise is isotropic in the angles, because this leads to easier formulation. So under these assumptions, the problem reduces to the phase dynamics, so the only important variable is the phases. And you can write down these phase equations. This is very classic, so nothing really important here. So you get to these equations here, where G, you can prove G is going to be a function like this. And the C naught here is very important. This is what we call shear in the oscillator model. Any question? No? OK, so now I said that we have a transition to synchrony. We have to be a bit more precise what we mean by transition to synchrony. I'll introduce as well what people call the Kuramoto order parameter, which is basically this quantity here. So what's important for us is this value of R, so which is a function now. So if R is very close to 1, means like all points, all phases, they are packed together. If R is near 0, this means that all phases are distributed. So this is the main quantity of interest now. So what I'm going to do, I write down these equations, I pump noise, and I try to compute this R as a function of the noise strength. So let me do one simulation example here before I start try to understand this problem. The thing is the following. So I have a power law network. The power law exponent is very close to 2. I have 5,000 nodes. I'm just coloring here the hubs so you can see where they are. And I'm assuming that the noise-free network does not synchronize. This is my main assumption. Yeah? So without noise, this problem is kind of very boring. So this means R is very close to 0.
For a certain coupling strength.
For a certain coupling strength, yes. Yes. And this is an interesting question, whether if you increase the coupling, the network would synchronize or not. But I'm assuming that now I have no synchrony for this particular coupling strength. Thank you very much. So now what I do, I pump noise everywhere, and here I'm plotting this as, so here is R, the order parameter. So here is the noise strength in the leaves. So shear gives me a frequency gap between rotation speed of the hub and the leaves. They are kind of around 9. And here I'm pumping more and more noise. So what you see, you start at 0. So what noise in the hubs is 0. There is no synchrony. Then you start pumping noise, you have a peak. And then you pump more noise, you decay. Yeah? So this is the effect I want to explain. And so first I thought this effect was trivial, because I thought this was coming from what some people know as this coherence resonance. Then I spoke to Ralph quite a bit. And I will call this effect coherence resonance, but this is not the coherence resonance effect that people know in the literature. So in the literature, people know what this coherence resonance is the following. So think you have a neuron. So if you kick, it gives a spike. Then you put a bit of noise, you excite this membrane, and then you see this concatenation of spikes. Then you can see a peak like this in terms of some kind of coherence measure. But here, everything's oscillating. I don't know. We didn't find a good way to interpret this in in terms that what people know. So this is the mean. In fact, I'm trying to convince you that if you pump noise in a heterogeneous networks where you have hubs, the hubs somehow transform this noise in a nonlinear way and can induce synchronization. Then if you are too greedy and pump too much noise, the hub actually filters this noise out and the noise effect disappears. And we observe this in a variety of networks. So I won't bother you here showing all possible simulations we can do. My goal here now is to explain this stochastic resonance effect. So if you see this stochastic somehow in italics, because I don't know. Let's call this stochastic resonance for lack of a better name. And I want to know also the scaling law for the optimal noise strength. So I showed you the noise goes through a peak. What's the scaling law? Okay, so this is my goal now in this talk. Is this goal clear? Any questions about the goal? No. Okay, so this problem is kind of complicated. It's kind of very hard to do any mathematics here. So what I will do, I will say, let me consider power law networks, which is kind of this Barabasi-Albert network, if you may, with the exponent between 2 and 3. So if the exponent is very close to 2, these networks, they're actually a concatenation of stars. So I might look at a single star. So it's what I'm going to do now. Okay, so I'll look for a single star, and then once I understand the single star, I'll put many stars together and form a complex network. So this is the problem I'm trying to understand now. So I have this star with all these hypotheses. I run the model. So now I do many tricks, which are standard, by the way, if you see. I'll do this phase reduction, then I do rescaling of variables. I do everything I can. I bring this model to a normal form. Once I bring the model to a normal form, this is the equations I get. So you see here I have some frequency spreading. So so var theta, they are the phases in the leaves. Psi is the phases of the hubs. So you see I have this beta now multiplying. So this beta now comes as a time scaling reparameterization of the hub variable. And here's my frequency spreading. So what's important here is that the scale separation, the shear effect comes here, and the noise now comes here. So what I'm saying, I cook this model in such a way for certain lambdas, such that this network does not synchronize, then I pump noise, I see a transition to synchrony. This is the problem I want to understand. Okay, let me consider a special case. Yes?
Sorry. Does the frustration parameter alpha play any role?
Extremely important role. At alpha equals 0, the phase space is foliated by invariant tori. The system is not hyperbolic. At alpha positive, you get some stability. Then you can use normal form and hyperbolicity. So alpha is a big player. And my alpha is always positive near 0. Okay, so I just want to mention this because there are many people here that work on this problem, so that they are not upset with me. So let me consider the identical leaf cases. So all leaves, they have the identical frequency, noise-free. Then this model that I just wrote can be written. I mean, you can change variables and so on. That it becomes like what people call explosive synchronization problem. Yeah, so there's some colleagues that work on this problem here that we can talk later. So this just a cue for some people, right? Okay. So if I do a change of coordinate now, so you remember I had leaf nodes and I have the hubs. I do this change of coordinates. I get new equations. And then a miracle happens. Because this is an impossible problem to solve. And now if I do this trick, I reparameterize time, I reparameterize space, I do this change of coordinates, I start massaging this equation. Then God look at us and say, okay, you might solve this equation using some very important trick. It's called the Riccati action. So actually you can solve these equations because there is a symmetry group, which is the Mobius group. So, okay, you can solve the equations. You can solve the equations by this Mobius action, and then you can compute the whole bifurcation diagram by using this what we call averaging theory, because you remember you had this separation gap in frequencies. So if you solve it, here's the bifurcation diagram that we get for the single star noise-free identical leaves. Here's R, here's lambda, and we can compute this analytically and everything. So many people can compute this analytically, by the way, by now. So what's important in this diagram here, you have two critical transitions. So you have, if you follow this branch here, you are in the asynchronous state until this point when you tip to full synchrony. And then if you follow this branch here, you follow this branch until here. If alpha is 0, nothing happens. If alpha is positive, then you drop. So this you can prove. So this is really a discontinuous transition. But what's important for us now is the following. So you see this region here. In this region, there is a lack of synchronization. Yeah? So the first thing I want to try to convince you, if I pump noise in the hubs, there will appear a synchronization branch in this solution. So what I mean is the following. So I have identical noise-free leaves. I pump noise in the hubs. I have a new branch of solutions. They will be stable because of the noise. So how do we do it? And this you can prove, by the way. This is a theorem. So the synchronous branch is almost surely stable and attracting for all positive lambda. So in picture means this here. So this branch was stopping here. So once you pump noise through the hubs, this branch continues all the way to 0. It's kind of, I don't know. So the proof is not complicated, so how do we do it? If you use this Mobius action, I can write down the differential equations for theta, which is the main phase, and for R. If you see here, this main phase is a very fast variable, and the noise only acts in theta. So this R will become stochastic variables through the coupling with theta. Okay, but because we're interested in special solutions, which is R equals 1, you can solve this. So you can write your Fokker-Planck equation and compute the stability exponents. So in particular, you can linearize around 1 and compute your Lyapunov exponent, which is given by this number here. And we can prove this is always positive for all lambda larger than 0, for all small alpha positive. So this means like this branch, just because of the noise, this branch continues. And we call this noise-induced synchronization. So now I'll continue this analysis with this noise-free version of the problem. So all leaves, they are noise-free, but I include now frequency dispersion. Okay? And you see this is more analysis I've done with the continuation of this branch. It does not explain the drop that we have as we pump more noise. So before I crack the machinery and show you the equation, let me try to convince you that this effect is kind of obvious or is kind of intuitive, okay? So the argument goes as follows. So it will be a back of the envelope argument so you can see the feeling of what has to enter in the formulas. So let's say all the leaves, they're in an incoherent state. So they're all asynchronized. So if you make this assumption and you write the equations and I say my leaves, they're all asynchronous, then what will happen is that the hubs, they decouple from the network, okay? So this is very easy to do. You can do it at home. And then, but then the hub will be driven by this Wiener process here, which is basically the hub frequency plus the Wiener driving, okay? And now basically we're saying the following. So this picture is not true, by the way, but let's assume and do this back of envelope calculation. So now the hub is forcing the leaves through this stochastic driving, okay? So if you write down the leaf equation now, you can expand in Fourier and so on. What you get is the following. So you get the oscillation frequency of this guy. You see now that the hubs, they are driving this phases now, but some kind of through a nonlinear function with the sign. So somehow the network, the coupling filters the Wiener process that the hub's trying to drive. Okay, so this is what we want to understand. Now we want to understand the action of this sign filtering this Wiener process. Okay, this is the stochastic driving. So for this, we introduce this process here. So let's consider the process that is Z, this is a stochastic process, which is precisely the solution of my Wiener action for the hubs. And then I introduce this correlation function, which, by the way, you can compute. This is a function of tau, no? This is classical. This correlation function and the power spectrum, they are Fourier pairs by this Wiener-Kitchen theorem. And in particular, the total effective noise is the integral of C. So you can compute the total effective noise by integrating C over time. So if you do it, this is what I mean. The total effective diffusion constant of this process is the integral of C. And if you crack the integral, this is what you get. So somehow this is hitting at the nonlinearity process that we saw. So you see, if you start pumping more and more noise in the hubs, the sign will filter out these fast oscillation. So basically it's the following. So you had you have a phase, and then you start shaking this guy stochastically quite fast, and then you apply sine. But because the shaking is too fast, you don't see anymore. So this is basically the intuition. And if you see, if I start pumping more and more noise, then my total effective diffusion constant starts decaying quite fast. And in particular, you can find the optimal. There is a problem in this argument. I like this argument very much, but this argument is wrong. Yeah? Because I said that the hubs, they decouple from the network. And this is not true. You cannot do a master-slave configuration here. But I like this argument because this formula actually explains the phenomena. Okay? Okay, let's go on then. So this is basically what I said. Pumping more noise in the hubs decreases the effective diffusion constant. Basically means like the leaves, they do not see the hub, so therefore they cannot synchronize to the hub anymore. I will just speak quite quickly about the full description of this problem. So the full description starts by noticing that you can write down the equations for the order parameters. So usually this equation is impossible to solve, right? Because you see, you take an initial condition in the torus, then you evolve under the flow. So this guy here is actually depends on all initial conditions you started and so on. But what happens here is the following, that if you start thinking a bit, this R is a very slow variable, will be stochastic variable, but changing slowly. And this theta here will be a very fast variable. Will be fast because of the shear. So if you don't have shear, they're in the same scales, then you learn nothing. But because of the shear, this phase here starts spinning faster. So this is the main observation that we have to do here for these order parameters. Let me tell you right away the implicit solution of this problem, because the idea is the following. So you can write self-consistency equations for R and theta, and if you run the machinery down the road, you get to this implicit form. So the solutions of these equations are solutions of this implicit function here, where you see you have to take the average. This theta depends on R, depends on G, depends on everything. Is the implicit formula. If you solve this implicit formula, then you find all the effect you need to find. Okay? So this formula you cannot solve analytically, but you can use root finding algorithms to solve it, and you can plot the level sets of this function and so on. Let me tell you how I get to this solution here, which is the solution of this problem. The problem now is computing this average here. And the problem is also the meaning I'm giving to this average. So let me go through this. So the goal of this slide is to show that there is a formula and how to obtain the formula now. So to obtain this quantity here, what I need to do, I need to create a theory that solves this average. And how do we do it? We use this, that these two systems, they're not in the same scale, so I can do a diabatic approximation to the Fokker-Planck equation. And then I can solve Fokker-Planck equation by what is called continued fraction solution to the Fokker-Planck. So this is what I meant. So we're going to solve the Fokker-Planck equation adiabatically. I'll say in a second what I mean. What I mean, okay, let me say now. Adiabatically means the following. So R is a slowly changing function, and theta is a fast changing function. So I fix a given time window, I say R is constant, and I solve the Fokker-Planck equation for theta. Then, in the next time window, I take the mean contribution of the phases. You can do this. There is a theory, it's called the stochastic diabatic approximation. So then you solve these iterations, and eventually you converge to the solution. And then finally, to find the solution, you use continued fraction expansion. So how do we do it? We write down the Riccat's equations. So this is another way of writing the equations I started with. Then I'm already writing the Fokker-Planck in Fourier space. So what I do now, I say I'm at equilibrium. And what I do is start recrafting the Fokker-Planck equation so that it appears in the form is suitable for me. So once I start massaging this equation, I will write this term here as x times OK. This is mu k, by the way. And then this is a classical problem. There's people found the solution in continued fraction in 86, if I'm not mistaken. I think in Risk in 88, he has in his book, for example. Okay, so we read from the book. This is a classical expansion of this formula, of the moments of your distribution. And if you pass the limits, you can find this in terms of hypergeometric functions. So this means like it's very well understood. So for our problem, this is what we obtain. We call Fox-in-Sox formula, because you can see here Fox. This is not my bet. It's Ralph Tonies. He wanted to do it. Okay, so in his honor now I'm doing. So you can find all the Fourier coefficients in terms of this Fox-in-Sox formula, and this Fourier coefficients you can find by solving these hypergeometric functions. So this means, okay, we are done. Now I just crack this function and I see the level set and so on. Okay, let me show you one case of prediction. So here's another network, 5,000 nodes I had. Gamma is a power law graph, gamma very close to 2. Here's a sketch of the network. So here we do, I think 1 million simulations of this process. And then in black, you see the histogram, okay? Because this is okay, so I'm plotting the histogram over time as a function of, for each fixed D in the hub, I plot the histogram, because now R is a stochastic variable. So the histogram will be a solution to the Fokker-Planck equation, which I can calculate now and so on. And in green is the theoretical prediction, which is quite good. So in particular, yes?
Sorry, to how many of the hubs you have to?
I pump noise everywhere. Everywhere, also in the leaves.
Oh, I see. Okay.
But this is an interesting question because up to now, in the simulations, I pump noise in the leaves. But in the calculations I've done, there is no noise in the leaves. But we can, okay, I think the next slide solves it.
What will happen if you didn't pump the leaves?
Okay, so the idea is the following. Okay, so you can find the scaling relations for this resonance. So this kind of, and this is the main thing. So adding noise to the leaves has the same effects as frequency spreading. And this you can, okay, philosophically speaking, is not the same, but if you crack the calculations, at the end, you see that they have precisely the same effects. There is no difference in the mathematics. So either having frequency dispersion in the oscillators or pumping lots of noise, they have precisely the same effects. Nothing will change. So, okay, so my message to you today is the following, so that once you have a complex network, let's say networks with hubs and so on, and you pump noise, then depending on your assumptions of your original model, the noise and the network structure can interact, actually. And the network structure can work as a nonlinear filter for this noise process. And then you can have noise plus structure enhancing collective behaviors, okay? So hubs plus optimal noise will enhance your collective properties. Thank you very much.
So thank you, Tiago.
Your parameter R never reached 1. That is normal. But my question is, do you have a giant component that not all are synchronized, or is there some fluctuations and all are synchronized?
So the idea is the following, so because they are all stochastic variables now, so they can join this giant cluster and then escape, oscillate a bit with different frequencies, then join again. So usually this is, if I have to do a movie, this is what you would see, some nodes there.
All are included.
No, the idea is the following. So if we draw in the, so if this is the circle, I guess this depends on the run as well. And then we plot here the phases. The phases, they should be originally they always spread out, and they're rotating. Then you include noise, they all come here. But some people are very stubborn, they rotate with faster speed. And then they rotate, and sometimes they join this cluster for a while, and then they escape again. So this is the, but they don't have two groups. So they stay one group. By the way, breaking two groups is not a problem for this formula because we compute all the momentum of the Fokker-Planck equation.
Thank you for the talk, very nice. I was wondering how general do you think this phenomena is and how it depends on the shear, or if you think it could be adapted to any kind of model, dynamical model, or what is your impression about this?
So I think it's as general as it gets, so it only depends on your assumption of the original model. So basically, the idea is the following. Take your explosive synchronization transition and pump noise into the network, you see this.
Yeah, probably yes.
No, this is the answer. And now the question is the following. How to get to explosive synchronization? I'm saying include shear in your oscillator model.
Okay.
Any other questions? Okay.
You've taken Kuramoto oscillators. What happens if you take, let's say, Stewart-Landau or
It's the
Rössler?
same. It's the same. Because the Stewart-Landau is a normal form for the Hopf bifurcation. Yeah. If I now run the phase reduction for the Stewart-Landau, I get the Kuramoto model. Yeah. So the interesting thing is like, which I don't know the answer, and we didn't try, is, for example, if you take a relaxation oscillator. My guess is that nothing changes. But then the phase response curve for relaxation oscillators, they are discontinuous. And then maybe some new phenomena will appear. If the phase response function or curve of your system is continuous, then you can expand in Fourier, and the same will happen. Yeah. But it's a very nice question. I didn't try to.
Okay, thank you, Tiago.
It's my pleasure to be here again.
So we can proceed now with Ulrike Feudel from Oldenburg.
Okay.
Let's hope it works.
So we need this.
Do it again?
Yeah. So where is this thing here? So not working, no? So we tried it out, and so HDMI was it. So it worked in the break, sorry. We tried it out. Yeah? So.
Estava funcionando a meia hora atrás.
Can we turn up the microphone? Yes.
Good. So something. So we have to get out here again. And so sorry for the delay. So we tried it, but you see, technical problems are always on the way. So first of all, I would like to thank the organizers for inviting me here. So it's my pleasure to be here. So as Ram already mentioned in the introduction, so I was already part of the first one of this series of conferences, and it's always, so to say, fun to be in this conference. Now, so what I would like to talk about today is joint work with a couple of people from Brazil. As you see, Everton Medeiros did most of the work here, so he spent quite some time with me in Oldenburg, but it's also a collaboration with René Medrano, Iberi Caldas, who is in the audience, and Tamás Tél from Budapest. So I would like to talk about transient chaos in networked systems. So this is something which has not been a lot addressed in the past, and I would like to focus on two different things. One of them is desynchronization, and the second one is real-time vulnerability. I will just explain what I mean with this. Now, so this is, of course, known to almost everybody here in the audience. So synchronization is a problem which has been tackled for decades, I would say now. So where people think about so the adjustment of rhythms due to coupling for different oscillators, and there are lots of different applications, starting with the synchronization of clocks, so already in the 7th century. But nowadays, so to say, these are very famous examples which are shown all the time. So therefore, I'll skip this here and go better to what is really important, so to say, in synchronization, because one of the main problems is really the loss of synchronization. So that synchronization breaks down. This is a technical problem, for instance. Here is the famous blackout, which is in the power grid of the United States. And there are tons of papers, I would say, dealing with this kind of breakdowns. And so what people usually study is that they change topologies and say, okay, so we remove nodes, we remove links, or we add some links and study the conditions under which, so to say, such a breakdown happens. So I would like to focus on a different things, and this is perturbations of state variables. And this is also, of course, done in the past. And so when we look at this stability theory of networks, or particularly the synchronized states in networks, is also something which has been tackled by many researchers. So there are local stability measures like the master stability function. There are global stability measures for the synchronized state, like basin stability, or the distance to the basin boundary, or minimal fatal shocks. So this is all done for many years already, but our aim is something completely different. So because we would like to ask the question, what happens really if I have transient chaos in my system? And how does it really, so to say, influence synchrony so when this kind of transient chaos appears? So what is transient chaos? So we had that already here in one of the talks. It was mentioned already today. So what does it mean is basically so that you have a chaotic set which is in the state space, but this is an unstable set. That means it has properties like a saddle, for instance, and most of you will know, so to say, what a saddle point is. It has stable directions, it has unstable directions, but it's unstable, so to say, in the dynamics. And this would be one of the examples of such a chaotic saddle. And so the basic property here is that a chaotic saddle is an unstable object, and that means that all the points, so to say, any trajectory which is close to this chaotic saddle will escape. And this was also mentioned already, and there is a certain scaling which is available here, so to say what you can compute, basically that there is an escape rate from this chaotic saddle, and all your trajectories finally will leave the chaotic saddle. So when we look at this transient chaos, so this is first of all the explanation, what is it? But where does it come from? So what are the situations where we have this kind of transient chaos? There are several possibilities where you find this kind of transient chaos and these chaotic saddles. First of all, so to say, whenever you have fractal basins of attraction, then there is a chaotic saddle embedded in the basin boundaries. And so here is an example. So these are two coupled logistic maps. So all the color coding indicates different attractors and their basins of attraction. So we have 5 different attractors here and 5 different colors. And the black stuff, which is here on top, is the chaotic saddle, which is embedded in this basin boundary. So this is one of the possibilities. A second possibility is that the chaotic saddle emerges as a result of a boundary crisis. In a boundary crisis, a chaotic attractor disappears. But of course, this is an invariant set. It does not disappear into nowhere, but it is still there after the boundary crisis, but it's unstable. And you would see after the boundary crisis, so to say, you would still see this invariant set embedded in your state space, but it's embedded in another basin of attraction. Here we have another example. So this would be the Ikeda map just for you for illustration. So we have 2 attractors. One is here, one is here. And so this was a period 3 orbit, which underwent, so to say, a period doubling cascade ending into chaos. And then there is a boundary crisis, and what's left is this chaotic saddle, which you see here. So this is the second possibility, how this can happen. And the third possibility is the one here below, so which happens in all different systems which have either a period doubling cascade or a period adding cascade. Wherever you have this kind of windows, where you have a saddle node bifurcation where a periodic orbit appears, and there is, so to say, a chaotic attractor here. It's not visible here anymore, but then the window is closing with an interior crisis. What you have here in the middle is also a chaotic saddle, which you don't see, of course, here, because it's an unstable set. And this is just an example for the logistic map period 3 window. So these are many situations where we can have this kind of setup, that we have this unstable chaotic set, which is in the state space coexisting maybe with some other stable set. Now, this is what we would like to consider. So we take, for instance, the Duffing oscillator, so which actually was introduced by a German engineer, Georg Duffing. So therefore, the name, the correct pronunciation, so to say, is Duffing. So I'm fighting for this. In a certain way, it's not the Duffing oscillator, as everybody says. And he was studying basically buckling of beams. And so this system exhibits different kinds of dynamics, periodic and chaotic. And there is also such a period 3 window. And we will focus here, so to say, on this periodic orbit. But this would be the shape of the chaotic attractor, which is along this red line here for another forcing amplitude. And this will play later on a role. So therefore, so keep in mind, so to say, how the shape of this chaotic attractor looks like. Now let's focus on this kind of situation here. And now put this kind of dynamics where we have a globally stable periodic orbit. There's no other attractor here. And we have this coexisting with a chaotic saddle. Let's put it on a network. Now, so before doing so, so to say, I would like to show you this kind of dynamics again. So to say, this would be the network now. It's a non-locally coupled network. You see here, so to say, we have this local neighborhood where different oscillators are coupled. And each of these oscillators is now in this period 3 window. There is a globally stable attracting periodic attractor here. And so there is a chaotic saddle embedded in its basin of attraction. How does it look like for this situation? So this is for 1 unit. So this would be a part of the state space. And this little part here is enlarged on this side so that you can see that we have this period 3 orbit. These are the black dots. The green stuff here, so you see this looks like the chaotic attractor, which we have seen in the previous slide, but now it's a chaotic saddle because we are beyond, so to say, the saddle node bifurcation where this period 3 orbit appears. And what is the gray stuff here, which is, so to say, covering most of the state space, is the stable manifold of this chaotic saddle. That means points which are starting there would be attracted along the stable manifold to this chaotic saddle, but then ejected from the chaotic saddle later on because it's unstable. So what happens now to synchronization? So let's have a look and start our network. Let it first evolve for some time so that it is synchronized, completely synchronized. All our oscillators are synchronized, so we have a network of 100 oscillators here. And then we perturb it. We perturb only one of the units, the one in the middle here, basically. And so we give it a kick and wait. OK, so what happens is, as you see here, so there is a slight disturbance. So some of the oscillators lose synchrony, but finally everything is restored. And we get back to our synchronization. So synchronization is restored. Here you would see it after 6,000 periods of the forcing. Now, when we slightly perturb this with another perturbation, something completely different happens. Even though this has only a globally stable periodic orbit, basically what we see is a complete desynchronization of the network. So with a very small perturbation, and the perturbation, so the deviation from this perturbation is just in the second component, and this would be the size. So it's 10 to minus 4. It's not much, and still we go, so to say, to a complete desynchronization of the network. So this is what we can see. And then we were asking ourselves, so to say, OK, so if one perturbation gives us this kind of behavior, let's try other perturbations and look how it looks like. And then, so to say, we take, again, only one unit and perturb it, and then we color code, so to say, to which of these final state it goes. It goes either to complete synchronization, so we have a restorance, or we have a desynchronization. And so we measure it by next neighbor error dynamics, and we introduce an order parameter, basically, so which is dependent on a synchronization quality here. And for complete desynchronization, this order parameter is 1, so this is yellow here. And for complete synchronization, it's blue, and this is the 0 here. And then you see that there is a fractal-like structure popping up. So we have here a structure where we have parts of the state space where there is a complete mixture. If we just enlarge this thing here, then you see, so there are blue and yellow dots all over the place, completely mixed. So one can quantify this, of course. And so the method to use in this case is what is called final state sensitivity. This is an old method, has been introduced by Celso-Gregorzi and co-workers in 1985. And what does it do is basically it measures the fraction of initial conditions, so which you perturb, so to say, by a perturbation epsilon, and you check the fraction which is changing from one basin of attraction to another one. And what you get is, so to say, this kind of behavior. And there is a scaling behavior here, so which has been shown already, so to say, by Celso-Gregorzi and co-workers, so that there is a scaling like this here, so that this fraction basically scales as epsilon, the perturbation, to the power of alpha. And from alpha, you can judge, so to say, the fractality of your structure. And then we see that there is a pronounced, so to say, change in what the structure is. Because for very small perturbations here, so to say, the yellow part is dominating, and then, so to say, the fractal structure between blue and yellow is dominating this slope here. If we would now go only for this one here, so compute the same thing here, so then we end up with a scaling like this. And so this alpha, which is called the uncertainty exponent, is very close to 0. And this is a strong indicator that this has a kind of riddled-like structure. For a riddled basin of attraction, you would get something which is very close to 0 here. And we are close to it, as we see, with an exponent 0.011. So that means, so this kind of behavior, what we find is something which has a riddled-like structure. Now, let me explain the mechanism, how it really works. So what happens here? So when we are perturbing our system, so what happens basically is, so to say, shown in this kind of cartoon. So we are having, so to say, first of all, all our oscillators on the synchronization manifold. They are completely synchronized, but one of them is kicked out. And if it happens so that this kick, so this perturbation, brings this kind of oscillator, so to say, in the neighborhood of the stable manifold of our chaotic saddle, then it will be attracted. And it might, so to say, because of the coupling, also take other oscillators with it, so that some of the oscillators are really on the chaotic saddle. Now comes, so to say, an interplay between different forces. So we have the restoring force, which tries to put the system back to synchrony. Then we have the coupling, so to say that neighbors influence each other. And of course, since we are on the chaotic saddle, small perturbations so of neighboring things would exponentially drive trajectories from each other. So that means that we get really two kind of outcomes. So on the one hand, we have synchronization, which would be, so to say, what we would get here. So we would get back to the synchrony. But we would also get desynchronization, where all our oscillators finally are spread on this chaotic set here. So the outcome of this interplay is not predictable. So there is a kind of, say, minimal number. It seems that there is a minimal number of oscillators which you have to pull with you, so to say, to get onto the chaotic saddle to make it completely desynchronize. Now here is again, so to say, so even with, so to say, the couplings between the different oscillators shown that everybody is now on this chaotic saddle. The question is whether is it still a chaotic saddle or is it now an attractor? This is something which is not clear so far, I would say. So even though we tried to get to this point, because, as I said, so a chaotic saddle is characterized by escape. So that means if I have trajectories which are on the chaotic saddle, they should leave after some time. That means if we are increasing integration time, so we would have a higher and higher probability that synchronization would get back. And this is what we tested. So these are, for each of these points, we tested a number of networks. So it's 128 to be precise, and checked, so to say, how many of those get to synchronization and how many are not getting back to synchronization. And then we see, so to say, that there is this kind of leveling off. So that means we have always a fraction which desynchronizes completely, so at least for this number of time units, so that there is an indicator that this is now persistent chaos. However, so from a dynamical systems point of view, there is no mechanism how this can happen. So at least we don't know really, so to say, how we can probe this. We are now working, so to say, on a simpler system than this one, just to get out whether this is now finally an attractor or not. Now, let me discuss the consequences of the same kind of situation in a completely different setting. And this is, so to say, the role of chaos, so to say, transient chaos for control. Let's think about something else. So let's think we have now a machinery which should work in synchrony, like a network, so to say, like a power grid. And there is a perturbation on it at a certain time instant. And we look, so to say, how this perturbation really, so to say, acts on this synchronous state. And we used here not the Duffing oscillator, but we used an electronic circuit because this is an experiment. So we hope that these guys are maybe picking up this idea and try to do it in an experiment. But the situation is the same. So we have a chaotic saddle, which is the red guy here. So there is a periodic orbit. You see it only, so one point of the periodic orbit you see only here, so to say, in the blow-up. And there is the stable manifold of this chaotic saddle, again, as we had this in the previous time. So now we are doing almost the same thing, but with a tremendous difference in such a way. We are taking now always the same perturbation, so for one of the units again, but we apply it at different time instance of our periodic orbit. So we have a periodic orbit, and we can so to say, make this perturbation at a time instant TP1, and then we can make a perturbation at a time instant TP1 plus delta T. So in this case, we go back to synchronization. So that means this perturbation here would get us into a point where, so to say, this is the basin of attraction of the synchronized state. But if we do it slightly later, so we get to desynchronization. And that means timing is something very important in this business here. And so that means we see that the system is vulnerable in real time. So it depends crucially on the timing when my perturbation is really, so to say, getting to my periodic solution, kicking it out. So for some of the time instance, everything's fine. We restore synchronization. For others, so it's not, because we go to complete desynchronization. Now, when we look at this, so to say, along this periodic orbit and color, so where along this periodic orbit we go to desynchronization and where do we go to synchronization, then we see, so to say, the blue guys here are the synchronization restored solutions. The red ones are the dangerous ones which go to desynchronization. And so now we see magnifications here, and from here again here, and we see the more we zoom in, we see more of a fractal structure. That means we cannot even, so to say when we go to desynchronization and when do we restore synchronization. And it seems that this is completely mixed, because every new zoom, so to say, gives us a new structure, and that means there is a fractal-like structure, so whether you're safe or you're not safe. And we can measure this, of course. We try to quantify the whole thing. So how do we do that? So we look at different time instance, subsequent time instance, but also other time instance which are further away, and check the following properties. So of course, so in our state space, we look at a certain box, so where we put our perturbations. So this is a given box, and we have there, so to say, two different, or say three different behaviors. We go back to synchronization, we go to complete desynchronization, or there is also another attractor at infinity, which I have not mentioned yet, but this also happens. And then we can look at two different kind of things. So we can define a safe set, and that means these are all these perturbations which lead to restoration of synchronization. This is, of course, a subset of the basin of attraction of the synchronous attractor. So, and this safety index measures the fraction of perturbations which stay safe even after the time delta t. So we measure it once, so to say, at time t, and then at time t plus delta t, and measure how many of those points which have been safe at time t are still safe at delta t. And we can also compute the basin stability, so which measures the fraction of safe perturbations with respect to all the perturbations. We have the safe and the unsafe ones. Now, how does it look like? So this is what you would get out. And the white stuff here, so the box we have chosen is this rectangle which is shown here. everything what's white goes to infinity. So this is a part of the model, so to say, that infinity is an attractor. But for us, it's only interesting to have the red and the blue points here, because the blue points are the safe points. So they lead to restoration of synchrony, and the red ones are the unsafe ones where you go to desynchronization. The first thing what we see that there are many more red points than blue points, and then these are the subsequent time instance, and we see, so the set looks, on first glance, quite similar, but when we look, so to say, in more detail, so we would see that this point here changes from one color to another one. And if we look at base instability, so we don't see much of a change. So this is almost the same thing, but so we see that the safety index tells us that only 70%, a little bit more than 70%, stay safe, and 30% are totally changing. We can do the same thing so at another time instant, and we see the same kind of behavior. The percentages are a little bit different here, but now we see, of course, if the time instants, so to say, are far apart on this periodic orbit, so then we see also some kind of changes in base instability, and also these percentages are changing. Now we can look, so to say, at how long does it take so to restore synchrony or having so desynchronization along a period. So this would be one period. And then we see, so to say, these would be the times which it takes to restore synchrony. So for the blue ones, the red ones, for even this high number of periods of the time in, so to say, the time forcing is then no synchrony at all. So this is complete desynchronization. So this brings me to the conclusions. And so as I would like to show you here is really that transient chaotic dynamics, which is embedded in state space, can play a rather important role in the business of whether so you have synchronization or desynchronization. So because any perturbation can bring you, so to say, to the neighborhood of the stable manifolds of the chaotic saddle and bring you to chaos, and this chaos will, so to say, be manifested either for extremely long transients, so that we cannot see, so to say, the escape, or even to an attractor, which is still an open question to study. And we see also that the whole perturbation business is also phase-dependent along the periodic orbit. And this tells us also, so to say, that next to a safe point, there could be already an unsafe point, which gets us to desynchronization. And therefore, these systems are extremely vulnerable with respect to perturbations whenever these chaotic saddles come into play. And this is not an exotic situation, because I have shown you when we have to expect this kind of chaotic saddles, and there's a lot of system classes which possess this, and these are all systems with period doubling and period adding cascades. So that means we have the whole class of excitable systems here. We have all the period doubling systems here, and of course all the multistable systems where attractors appear in a saddle node bifurcation, undergo a period doubling cascade, end up in chaos, and the chaotic attractor disappears in a boundary crisis. So this also adds here to all these system classes. That means this is a phenomenon which occurs in a large class of systems and has to be taken into account. Thank you very much.
Thank you, Ulrike. So, questions?
Ulrike, thank you very much for the very nice talk. There is a work by Sandro Vallente. So the idea is the following. So you see the problem as you see, but you see as this extreme event case where you visit the diagonal. And he has a formula for this. So the visits to the diagonal. And this is like enters the extreme event category, blah, blah, blah. Only depends on the measure that's preserved by the system. So it's just a suggestion. So instead of doubling map, if you use the tend map, you can compute the measure and you can crack these numbers and see. Did you try it?
So we have not tried this, but to tackle the problem whether this is really an attractor or not, we are now switching to maps, because the period 3 window of the logistic map does the same thing. And there we have also some hope really also to compute the chaotic saddles, which I have not shown you for the high-dimensional system. Because I have shown you only the chaotic saddles, which are, so to say, for a single unit. And we are supposing that when we are coupling them, so that a huge chaotic saddle appears, but we cannot compute it. But for the maps, we might use the method which has been developed by, I think, Lenny Nusse and Jim York, so the stagger and step method, so where you can compute chaotic saddles for high-dimensional systems, and then we might see.
Because if you take a look at there's a piecewise linear map, and then Lai Sang Yang, she computed all the invariant sets for given topology.
Okay.
Then you have more.
Very good point. Yeah. Okay.
So my last question, so I don't want to, because the size of the basing, so let's say the transversal stability depends on the eigenvalue of the Laplacian, and for these rings, they tend to go to 0 as the ring goes too large. So you have a dimensional problem now.
So all this linear stability would not apply here. So because we are dealing with larger perturbations, and then all the linearization, which you would get where you can work with eigenvalues and stuff, would not apply here. So therefore, the eigenvalues of the Laplacian would not help.
Any other questions?
Is there something like an uncertainty exponent for these systems?
So what we have computed, this is an uncertainty exponent, but we were, so to say, pretending to know that this other thing is a chaotic attractor, which we don't know. So in principle, we have computed the uncertainty exponent for a set where we think this could be different basins of attraction, but so where this theory has been developed for. So we are not even sure whether this is an extremely long transient. But if we look at this problem, so to say, from a practical point of view, then you would never see whether this is an attractor or this is a chaotic saddle, because the times you need for escape are extremely long, and in an experiment you would never see it.
Okay, thank you again, Ulrike. So now our next speaker is Adilson Motter. Okay, yeah, put this out.
You mind if I try to make this work first?
So I will switch it off.